Hello everyone, myself Alok Kumar. I am assistant professor in Government College of Engineering, Dharmapuri. So here we will see next topic, that is recognition of tokens, and parallelly here we will see Lex program. So here recognition of tokens, this topic we will see. The starting point is the language grammar to understand the token. Suppose we are understanding tokens, so before that, so we should know the language grammar. So suppose here we have mentioned one example statement, STMT, if expression then a statement, if expression then a statement, else a statement, or empty. And expression is generating turn, relational operator RELOP, turn or turn, and term is in this grammar, term is generating ID or number. So here we can formalize the pattern. Next step to formalize the pattern. So here terminals are if then else, relational operator RELOP, ID and num generates set of string given by the following regular definition. Suppose here if, then we will say this one is normal, yes, if, then also, then, else also, here it will work as else. But here RELOP, so this one is relational operator, so these are less than, greater than, or less than equals to, or greater than equals to, or equal to, or not equal to. So here we have mentioned one by one like pattern. Digit, that is from that value can be from 0 to 9. Suppose we are saying digits, so that is digit clean plus, so that value can be either 0 from 0 to 9, but it cannot be empty. Letter means it can be from A to Z, either in uppercase or lowercase. ID, that is letter or digit clean star. And here optimal fraction, that we are saying dot digits, or it can be empty also. Optimal exponent, that can be E, and that is plus or minus digits, so that is exponent, or it can be empty also. And this one is num, that is generating digits, optimal fraction, optimal exponent. Okay, so this one we have seen. Now here optimal fraction is either a decimal point followed by one or more digits, or it is missing, or we can say an empty string. An optimal exponent is either an empty string, or it is the letter E followed by optimal plus or minus sign followed by one or more the digits. Okay, for this language fragment, the lexical analyzer recognize the keywords if then else as well as the lexeme denoted by relational operator RELOP, ID and num. Okay, so here now we will see transition diagrams. So it is a diagrammatical representation to depict the action that take place when a lexical analyzer is called by the parser to get the next token. Okay, when parser, or that we say as syntax analyzer, when it gets next token from lexical analyzer, at the time this take place, the action of this transition diagram take place. So transition diagram, suppose we have mentioned here for relational operator, you can see here this one is one snapshot we have taken for relational operator. This one is less than, equal to, and this one is, you can see, less than, this one is not equal to, and this one is for less than. Here you can see this one returning relational operator, and we have given attribute value as less than, equal to, LE. Here relational operator, and attribute value we have given not equal to any. Here less than, and after that here this one is equal to. So EQ we have given relational operator, this identifier, and EQ is the attribute value, and this one is greater than, equal to. So returning, we can say here relational operator, this one is identifier, and G, that is attribute value, and greater than, so GT we have mentioned. Okay, so this one is transition diagram for relational operator. And transition diagram, suppose we are finding for identifier. So this one is the transition diagram for identifier. So letter, and this one is letter or digit clean star. So here this one is returning the token whatever identifier, and based on that whatever ID we are providing, install ID. Okay, so now here we will see Lex, that is a computer program, or here we will see a Lex or a language for specifying lexical analyzer. Lex, this one is a computer program that generate lexical analyzer. So here in this one Lex source program, suppose we write here this one for Lex, suppose name we are giving .l, this is the extension of this Lex program, and this one we are giving this input to lexical compiler, and at the time it generate one file lex.yy.c. And next after that C compiler will take the input of this output of lexical compiler, and it produces as output as a.out. Here a.out is the lexical analyzer that is taking input stream as input, and it is producing sequence of tokens as output. So here we can say first a specification of lexical analyzer is prepared by creating a program lex.l in the Lex language. You can see from here, and after that lex.l is run through the Lex compiler to produce a C program lex.yy.c, and after that finally lex.yy.c is run through the C compiler to produce an object program a.out. That is a lexical analyzer that transforms an input stream into a sequence of tokens. Now here you can see the structure of Lex program. Here it consists of three parts. First one is declaration, and these are the symbols that we use in Lex program, and these are the translation rules will also be there. After that here these symbols we will use when we will write Lex program, and after that auxiliary functions also we will write when we will create one Lex program. Now here this next topic is finite automata. So finite automata already you have seen, but here also we will see it is a transition diagram that recognizes a regular expression or grammar. And if we want to give the definition of finite automaton, that is M equals to, this one is Q sigma delta Q naught F, where Q is finite set of states, sigma is a finite set of input symbols, and delta is a transition function that maps input state this one Q is the states and this input alphabet, and it is going to another state. Okay, and Q naught is the starting state, and F is the set of final states. So that's why we have mentioned F is subset of Q. Now here we have shown some finite automata state graphs, like this one we use for state. This one is starting state, this symbol, and accepting state we use denote with this one. A transition from one state to another state we have mentioned, like using A we are going from one state to another state. This one we say as transition. Another kind of transition, that is empty move from one state to another state if we are going using empty. So machine can move from state A to B without reading input also. Without reading means if we are, that is empty move is there. Suppose we are taking some examples. A finite automata accepts a string if we can follow transition labeled with the characters in the string from the start to some accepting state. Suppose we are taken one example, a finite automaton that accepts only one on input alphabet 1. So here you can see this one initial state and this one is final state. With 1 we are going. Another example, we have taken a finite automata that accepts any number of ones followed by a single 0. So you can see ones, any number of ones and followed by 0. So this one is finite automata. This one also finite automata. Finite automata can be of two types. One is DFA and NFA, deterministic finite automata and non-deterministic finite automata. So little difference is there between DFA and NFA. What are that? In DFA, one transition per input per state, or we can say transition function will be like queue from one state using one input symbol, we can go to that particular one state. And here there is no empty moves in deterministic finite automata. While in non-deterministic finite automata or NFA, it can have multiple transition for one input in a given state. Suppose for transition function, we can say from one state using one input alphabet, we can go to more states, and it can have empty moves. So these are the basic difference between DFA and NFA. So suppose we have taken one example and we have made NFA and DFA for both. We have made NFA and DFA for this language, a finite automata that accepts strings and with double zero, while input alphabet is 0, 1. So we can make NFA ending with double zero. So it can start with any one, either 0 or 1. So 0, 1, this one either 1 or 0, and this one is double 0. So this one, we can say this one is the NFA, all strings ending with double zero. And if you want to make DFA of this one, so this one is the DFA. So here all string will end with double zero, and string can start from either 0 or 1. Okay, so suppose any string is like 0, 1, 0, 0 also. So 0, 1, 0, 0 also it is going to accept. Suppose some string is 0, 0, 1, 0, 0, that also going to accept. Suppose one string is 0, 0, 0, that also going to accept. Suppose one string is 1, 0, 0, 0, that also going to accept. So here all string that are ending with double zero will be accepted with this DFA and NFA. So next topic we will see next unit, next lecture. Thank you.